All right, we're continuing with a deeper dive on running, and we're going to go through this paper here, which you should have downloaded and read prior to watching this video. And or watch the video and then read the paper and then watch the video again, but you want to watch the video after going through the paper. This is sort of a neat paper I found just recently, 100 marathons in 100 days. Unique biomechanical signature and the evolution of force characteristics of bone density. The authors are listed there. You'll notice that there's a bunch of zeros here available. Well, there's available online XXX, and there's some X's up here. When you see that, that actually means that this paper is available online prior to print. So this paper is ready to be published, but it just has not hit the actual hard copy paper version of the manuscript. So this is really something that's just coming out, and this is neat for a couple of reasons. One is to do 100 marathons in 100 days. That is incredible. That's 26.2 miles every day for 100 days. Obviously 2,620 some odd miles over that 100 days. So that's an amazing ultra event that someone has taken on and done. And there's other people have done this too. But that is really pretty amazing to get up every day and complete a marathon. And so what this group was interested in doing was understanding the biomechanics of this particular runner. So one, I thought the topic was really neat. And actually there's someone who right now in spring of 2021 is attempting to do 100 iron distance events in 100 days. And he's not following the rules specifically to an Ironman. That is, he's wearing a wetsuit while swimming in a pool, and he is biking with a group of people that allows for some drafting. So there's little things there, and he's doing some IV in between days, but still really amazing endurance of feat to cover 2.4 mile swim, 112-mile bike, and 26.2-mile run every day for 100 days. And it's taking him about 16, 17 hours for each iron distance event. So there's only 24 hours in the day. So he's only getting about 7 hours of recovery before starting the next one. So we'll see if he does it. He's about halfway through right now. So pretty amazing. And likewise, doing 100 marathons over 100 days is equally as challenging, because this is really such a demand on the body. And what's interesting is they refer to the case study as the Marathon Man, and I think they are, and I tried to find who this was, but I think this is the same person who he's actually referred to as the Ultra Marathon Man, because he does a lot of endurance events. And we've actually did some testing of the ultra endurance man, not for research purposes, but more for a TV spot. So it was sort of cool. So this paper struck me for a couple of reasons. One, the topic, obviously endurance event, running. It has some biomechanics. And it's a unique paper in that it's a case study, but they also compare his data with a control group of similar running styled people, or at least foot strike people. And so it's sort of lots of things wrapped up into one manuscript. And so I thought it would be a fun one to go through. So remember, my approach to reading a manuscript, I encourage you to do this, is to read a manuscript and make sure that you're writing down terms that you feel are important to the paper, but then also to your learning as well. And so as you go along, and this is what I do, I mark up the paper as I'm reading it, and I'll write notes even, and just try to really immerse myself in the content that's being presented here. All right, so let's look at a few things, and then go into some of the results. And like the other papers I've reviewed, there's a lot to unpack in this paper. And I'm really going to zero in on some key elements of the paper, really related to some of the things that we're covering in class. Okay, so they point out the obvious here. You can only do 100 marathons in 100 days if you avoid injury. So now the paper turns into a discussion of what injury mechanisms are present for running. And we know runners are susceptible to overuse injuries. And some variables that are related to or thought to be related to running injuries include peak vertical loading rate of the ground reaction force, estimated peak vertical ground reaction force, peak braking force, and absolute knee stiffness. So we need to know what each of these are. I've done a ground reaction force video for running, so you go back and watch that if these don't strike you in terms of how to pick these out. I actually went and looked up the reference that's associated with this phrase, estimated peak vertical ground reaction force, and I went and checked out reference 6, which is listed back here. I went and looked at that paper to understand why they were emphasizing the emphasis peak vertical ground reaction force. And what's interesting is the peak vertical ground reaction force came from accelerometer-based work. I've done a lot of accelerometer-based work, and I've posted a number of videos on how to use accelerometers to understand the stress the system's under. But there's plenty of references out there that just that do relate peak vertical ground reaction force and not necessarily estimated peak vertical ground reaction force. That variable, the peak vertical ground reaction force, is related to running injuries. So let me just quickly draw out those 4 variables. I'll do it on the back of this piece of paper here. So if we have someone run across a force platform, and I'm going to do just vertical force here in newtons, the person's foot would hit the ground, and we would tend to see something like this for ground reaction force. This is contact, this is toe off. So this is ground contact, and ground contact can be with the heel, the toe, could be the midfoot. But for this paper, they're going to zero in on heel strikers. And then this is the point where the toe leaves the ground, so we call that toe off. All right, and then we're off into flight here after this until the next foot strikes the ground, which would then have another ground reaction force. All right, some variables. Well, this would then be, just so I can illustrate, because this does come up in this discussion, this time that the foot's in contact with the ground, we call contact time. All right, and what's interesting is, okay, now I guess I will draw up the next one. If this is the right side, okay, and then if I have a force platform, I'll do it this way. Maybe I see the left side, I'll do it in a dotted line. The left side curve doesn't need to look just like the right side. Okay, this would be left. We would then look at step contact, all right, this flight phase in between the 2 foot strikes where there's neither foot in contact with the ground, and then left contact. And then we would have a subsequent right contact, okay? And I mentioned this because I did have to look up their equation that we'll see in just a bit, duty factor. What some references will do is refer to this as swing time for the right side, and then use that as the duty factor. Other references will use this time in here where neither foot is in contact with the ground, and we have that as flight, and then we'd have another flight phase over here between left and right. Okay, so those are just some different time descriptors of the gait. The loading rate, let's see, what have we got here? Loading rate, it's one of the variables here, is how fast the force is increasing over time. And so we would look at a section anywhere between this peak and contact. And we look at, in essence, the slope of this force time curve. So loading rate is equal to the slope of the force time plot. And there's lots of discussion in terms of how to represent that slope, whether you look for little sections of slope in this period, in this phase, or if you just take this point and ground contact and draw a straight line between those two. And there's all different ways to do it. But there's the essence of loading rate is to describe how quickly force is changing. And there's other references that will look at loading rate here, or maybe unloading rate, something like that. But when they refer to loading rate in this paper, they're talking about how quickly the force is rising in that area of the ground reaction force. All right, estimated peak vertical ground reaction force. There's two here that they may actually be referring to, is this peak here and then this peak here. And most references will state that this force here is likely related to running injury. Sometimes you'll see people talk about this force as well as being related to running injuries. This happens slower over a longer period of time and occurs around mid-stance. This is happening right after the foot strikes the ground, probably within 10% of this stance phase. We're going to see that real sharp rise in force initially. And peak braking force, I don't have that drawn here, and absolute needs stiffness. So for peak braking force, I would have to go to the ground reaction force in the horizontal direction. And I'll just call that AP, okay? Positive, 0, negative, with positive being a force moving, pointing in the same direction as movement. And typically we would see a ground reaction force in the horizontal direction to look something like this. Again, this being ground contact and this being toe off. And the area under this curve is similar to the area under this curve when someone's running, in essence, what we would say is constant speed. Speed is not constant. Speed is actually slowing down and speeding up during this period of time. But if you slow down just as much as you speed up, then you'll be entering with one velocity and you'll be exiting with nearly the same velocity if these two areas are equivalent. So we refer to this phase where force is pushing against the person moving in the opposite direction of the person moving, and we would refer to all positive forces as propulsion, pushing the person forward or pushing in the same direction as running. And so they're identifying the peak braking force as a potential variable to look at to explain injury mechanisms with running. And then finally, they mentioned knee joint stiffness. All right, well, stiffness is related to springs. And we characterize how stiff a spring is by how much force it takes to either compress or lengthen a spring. So, and that stiffness is showing up in an equation that looks like this. Force due to a spring is equal to this constant K times delta X. And actually, I'm going to put a negative sign there because what happens is this force of the spring is in opposite direction as the compression or the lengthening of the spring. All right, so what does this equation tell us? Well, let me draw this. Let me try to draw a spring out here. Okay. Think of this as a spring. That's not a great spring. Okay. And then I'm going to take this spring and I'm going to compress it. So we're going to have these loops closer together. Okay. Something like that. Okay. So compressed. And this is, I'll call it resting length, or no force, or no force either trying to compress it or extend it. I could then look at how much this spring compressed as delta x, okay? This K represents how stiff that spring is. If that spring is really stiff, really hard to compress, that K is going to be a big number. If the spring is really not very hard to compress, it doesn't take much force to compress it, then that K is going to be really low. And what the way I can describe that is if I do it this way. If I put in compression on this x-axis, and over here the force that it takes to compress that spring, I would get something that would look like this. That as I increase the compression, I need to push harder and harder and harder against the spring. The slope of the force displacement plot is equal to the spring constant. Okay, so that slope is the spring constant. If I have a less compliant spring, it'd be something like this: lower slope, meaning it takes less force to get the same amount of compression than this spring here. So same compression, this took more force than this one. This is more compliant spring, okay? If I had a stiffer spring, I'd obviously be over here, something like this. If I wanted to get that same compression the way I'm drawing this, I'd have to go all the way up here, all right? All the way up here, here we are, all the way up here. Now that force up here, which is on the same scale, that's a lot of force to get the same amount of compression as these other two springs. This slope is really steep. That's a stiff spring, okay? So that's the essence of a spring. Well, in running, we often describe running as using this model of a spring to describe what's happening to the runner while the person is on the ground. So what happens in running? Well, the person strikes the ground like that, and then at some time later, I'll put this as time 1, I'll just put time 2 here, the person's foot is still in contact with the ground. Oops, that's the other foot, okay. And now they've gone lower, their center of mass is lower at this moment in time. And we could conceptually think of this as compression delta x of a spring, because then what happens? Then at some time later, we go through extension, and ultimately the person leaves the ground. So this is the other leg. Okay. And so now we have this, oops, I didn't do a good job. I should call it all the way up here. Now we have a recoiling of this compression. In essence, we do a really good job, or we can use this mass spring model to really represent what's happening kinematically and kinetically with the runner, just by looking at this compression that's happening here during stance phase. Now, there's different ways to do this stiffness. The way I've drawn it here, we would call this vertical stiffness. Okay, this is just one model to describe the stiffness of the lower extremity. Another way is to draw a line straight with from the center of mass to contact, and then you're aligning more with the leg, and you're looking at how much anatomical compression there may be in line from here to then here, and then recoiling over here. All right, then if we did that, we would call that leg stiffness. So just another model. All right, either way, they're both modeling the lower extremity using this equation and trying to solve for K, where F ends up being the ground reaction force and delta X is the amount of compression that the center of mass, or how much change, really, it's this one up here is what we're looking at. How much change in the center vertical displacement for vertical stiffness there is for of the center mass. Leg stiffness is more the resultant displacement that you're seeing. All right, but this is the number that we're keying in on. And now think about it this way. If the person is stiffer, they're going to go through less knee flexion, probably less hip flexion, less dorsiflexion. All right, there'd be less flexion overall of the joints of the lower extremity. If the person's more compliant, that would mean that they go lower in their running gait, and they would have more knee flexion primarily, maybe more hip flexion, maybe more dorsiflexion. But the knee is going to be really the key joint to be looking at when we start trying to describe stiffness. All right? So a stiffer lower extremity would be less knee flexion. And I'm focusing on the knee. A more compliant, or a spring that's easier to compress, is more knee flexion. Okay, so more knee flexion. And likewise, the idea of a spring is that if you do get a certain amount of compression, you also get some return force. The fact is, the lower extremity is not a spring. It just happens to behave very mathematically like a spring when we use this very simple linear mass spring model. Okay. All right. So that's vertical stiffness, and there's a couple of different ways to get to that vertical stiffness. Oh my goodness, I messed up all my manuscript now. Oh, that's really bad. Okay. Okay, well, I guess I should have used a pen. I'll have to print it up again, and you don't want me to scan that, that's for sure. All right, so where were we? Let's see. I am just in the introduction, and oh, okay. I'm going to go through the introduction. I'm going to stop there, and then I'll start another video for the methods. All right, so I was just describing the variables related to injury here. So we've gone through ground reaction force, braking force, and knee stiffness. Okay? An absolute knee stiffness, just because technically it should be a negative number, so they're just calling it absolute. So it's always positive. All right, sorry, now this is all marked up. You're looking at the mirror image of what I wrote on the back of this. All right, so another term I highlighted here is knee eccentric joint work. All right, so this is a new parameter that I have not described yet, but we have talked about knee eccentric joint power, eccentric joint power. This is going to be the same concept, but now we're just going to be calculating work. Well, my notes are all messed up now. So let's see, where am I going to write that? I guess I'm just going to over here, and I'll write it up here so I don't mess up too much. All right, we know work is equal to force times displacement. Okay. Eccentric work implies now we're talking about angular movement, and I say angular because we're talking about in vivo. So if we're having eccentric work, that means the joint is rotating. And so the implication here is that we are dealing with angular motion. So now work, another way to look at work in the angular world is to do the joint moment times the angular displacement. So T theta. All right, so that's just another way to do this. Now we're going to look at just eccentric work as the torque that is just due to eccentric contractions times the theta that is happening for that eccentric contraction, theta of one particular joint, for example, e.g. the knee. Okay. And again, e.g. here, the knee. Okay. So we would look at just the joint moment happening at the knee during the time that the joint moment indicates an eccentric contraction, which we'd have to look at power at that point, times the angle that is happening for the eccentric contraction as well, or the range of motion, multiply those two together, and then we get joint eccentric work. Okay, so taking the linear form of this equation and making it, turning it into the angular portion of the equation. All right, I'm going to stop this video there. I'm going to do this in different sections, okay? And I'll pick up on the methods next. Okay, thank you.